So next speaker is Professor Ite Albert Yu. So Professor Albert Yu received his PhD in physics from MIT in 1993, and he's currently the chair professor of the Department of Physics at the National Tsing University. Professor Yu has been leading a pioneering experiment group working on quantum optics, quantum information manipulation, electromagnetic induced transparency, EIT, slow light, even stop light, low light level nonlinear optics. He had done many groundbreaking work in these aspects, and he has also proposed and experimentally demonstrated new schemes for photons reaching another photon inside atomic media. His work in EIT-based light storage paves the way towards long-distance quantum communication and optical quantum computing. So he's also in the Taiwan national team, and he has also received numerous honors, like a fellow of the Optica, fellow of the Taiwan Physical Society, as well as some multiple winners of outstanding research awards. Let's welcome Professor Yu.
Okay. Thank you very much for Minxian's very nice introduction. I think the time is 1:55, all right? Okay, I have 25 minutes. So first of all, I want to thank organizer invitation. It's my great honor to give a talk in Hon Hai's next forum, especially with such a nice logo here. So in this talk, I will present our recent work on developing a narrow line width and high generation rate source of flying qubits. Right? And the flying qubits here, I mean the single photon carrying wave functions or quantum state. And because the photon really fly fast, so we call them flying qubit. And in my talk, this single photon, a heralded single photon or biphotons, which I will explain later, and we generate land with a hot atomic vapor. So in Taiwan, I have been known as a pioneer of the co-atom experiment. So today, I'm very delighted to announce we can convert the knowledge and experience learned from the co-atom experiments into some very nice result of hard atom experiment. So because the system of hard atoms is more practical in the real world application. So I will start with a brief introduction. Okay. So what are biphotons, heralded single photon? Actually, the two names indicate the very similar things. Biphoton is a pair of time-correlated single photon. As we know, single photon are the qubits. However, single photon appear randomly because we know exactly the number of photons, so the timing will be very random. So it's very difficult to use such a qubit in the random timing. Okay, and biphoton also appear randomly, but nevertheless, we can use the first photon of biphoton pair to start or trigger a quantum operation or quantum process. Then we use the second photon or second single photon in that operation quantum process. So the second photon is called heralded single photon. So you have a heralding photon, you have a heralded photon. So this make the quantum operation or quantum process become very convenient and very useful. So a commonly used mechanism to generate biphoton is the spontaneous parametric down conversion. After you have heard Zhisong, the previous speaker, briefly describe how to use the nonlinear crystal to create biphotons or pair of signal adder photon. This makes my introduction very easy. So I only want to emphasize this process is induced by vacuum fluctuation or the virtual photon in the vacuum. So we add the word spontaneous in front of a parametric down conversion. Okay, so it's abbreviated as a SPDC. So typically the media are the nonlinear crystals, and this is a very convenient and practical media. And the first literature report SPDC biphotons was reported in 1970. Okay. Another very commonly used mechanism to generate biphoton is the spontaneous four-way mixing, and it consists of two Raman processes. So again, the vacuum fluctuation will induce a Raman transition, and the population will absorb a Planck photon and emit a signal photon. At the same time, it will generate a ground state coherence between the state 1 and state 2. And the coupling field will utilize this ground state coherence to generate the second single photon, and we call it pro-photon. So again, you have signal photon, you have pro-photon. And for the second Raman process, because there's nearly 0 one-photon detuning, so it exhibits the effect of electric magnetic-induced transparency. As Ming-Xuan just mentioned, this mechanism, this effect, is arising for the slow light and stop light. So the pro-photon will propagate very slowly. So it is heralded photon, and signal just propagate at the speed of c, which is the speed at the vacuum. So the typical media are atoms, co-atoms, or hard atoms. So first literature report the SFWN with the co-atom in 2005. And the first hard atom result was reported in 2016. Right. So the co-atom system behave like an idea and a simple model. So I will use a co-atom experiment to illustrate the biphoton generation and the biphoton wave packet. So in the biphoton generation, one will apply two laser beams, a coupling field and the Planck field, to the atoms. Then the two single photon, signal photon and pro-photon, are generated inside the atoms. Again, signal photon propagate very fast, so it's a heralding photon. So it will move out the atom first and decay by the single photon counting module, abbreviated SPCN. Then the signal of the SPCN will send to a time taker and trigger this time taker. Pro-photons are slow light. They propagate very slowly. So after the time taker is triggered, then the second SPCN detect the pro-photon, will send a signal to time taker, and this time taker will record the arrival time of the pro-photon. So we call it a coincident count. So you have a first count due to the signal photon, you have the second count to start or trigger the time taker, and you have second count from the pro-photon. So we call it a coincident count. So here are the typical data showing the coincident count as a function of delay time between the pro-photon and the signal photon. And circles are the coincident count. And actually, this is a green line. Is the result of 4-point moving average of the circles. We reduce the fluctuation. And red line is the theoretical prediction. And in the inset, the square and the blue line are the Fourier transforms of the circles and the red lines. So just showing the spectrum of this biphoton signal. So we can see this coincident count as a function of delay time as the biphoton wave packet psi square. And psi is the wave function of the two photon correlation. And in this data, the temporal width of this biphoton wave packet is about 0.6 microsecond. And their Fourier transform just give you the frequency line width of 1.2 megahertz. So now I show you the biphoton data with the narrowest line width in the world. Actually, the reason we can achieve such a nice result because our co-atom experience system can have a very low decoherence rate or very long coherence time. And also we have a very high optical depth. That means the interaction between the photon and the atoms are very, very strong. So we can produce such an ultra-long biphoton wave packet. So I will use this data to illustrate or explain the biphoton wave packet. So ideally, the biphoton wave packet is a square pulse. So the left edge of this square pulse represents a pair of photons is created at the exit of the atoms. That means both immediate move of the atoms and detected by the SPCA. So signal photon and prophoton, heralding photon, and heralded photon has 0 delay time. And the right edge of this square pulse represent a pair of photons is generated at the entrance of the atoms. And the signal photon propagate very slow, very fast, speed of c, just immediately detect at time 0. And the prophoton is slow line, propagate very slowly. It takes about almost more than 10 microseconds to propagate through the entire medium. So there's a large delay time here. However, in the real experience system, you have finite coherence time. So the top of the square is not so flat. So there is a, okay, so the width of this square pulse is just the propagation delay time of the slow line. And the top, due to the finite coherence time, it will decay slowly. And the right edge will propagate through the entire EIT medium, the atoms. So it will limit it by the EIT bandwidth. It will become not so sharp. It will become smoother. So in this experimental data, we have a very long coherence time, about 43 microseconds, and propagation delay time is about 60 microseconds. And the EIT bandwidth, the reciprocal of the EIT bandwidth, corresponds to about 2 microseconds. So there's a 3 time scale here. All right. So because this biphoton data is very determined by the propagation delay time, so the Fourier transform of the data is very close to the square of the sinc function. And from the temporal profile, about 30 microseconds, also by this Fourier transform, we find out the line width is only 50 kilohertz. So this is the first experimental data with the biphoton line width below 100 kilohertz. So here is the table showing all the biphoton source in the world with a line width less than 1 megahertz. So this is our data. The narrowest line width and the longest temporal width in the world. And so such a narrow line width is very useful. For example, so we know such a long wavelength biphoton or heralded single photon can interface the superconducting qubit, all right, driven by narrow line width microwave. Also, such long temporal profile or narrow line width by heralded single photon can interface ion qubits, okay, because ion qubit typically utilize a very narrow transition. So for example, sometime later, Hon Hai can have its ion superconducting computer. I'm sorry, not superconducting, ion quantum computer. So maybe we can send out a biphoton wave packet with very narrow line width, and this biphoton wave function is a part of entangled photon. So they can run some calculation, but they do not know what our purpose of calculation. So that's some kind of very nice feature of this long wavelength biphoton or heralded single photon. So, however, the duty cycle of the biphoton generation with co-atom is very low. So in our case, it's only about 0.8%. That means we can only create 30 pairs per second in the co-atom experiment. So such a low generation rate single photon source is not very convenient for us in the experiment for our other experiment in the lab. So we decide to produce or develop the high atom biphoton source. I will describe some unique feature of our high atom biphoton source. So the previous SFWN biphoton generation utilized the counterpropagating configuration. So in the counterpropagation configuration, the coupling field and the pro field propagate in one direction, and the Planck field and the signal field propagate in the opposite direction. So the sum of layer K vector is given by two absorption and emission process. The first one is absorb the Planck photon, emit the signal photon. So you get this K vector plus K vector minus K vector. And the second absorption emission process is given by this coupling and pro absorption emission process, absorption coupling field, emit the pro photon. So we just write down layer K vector in the counterpropagation scheme, and omega 21 is just the frequency difference between two ground state, which is 6.8 gigahertz in our case. So after we write down this value, we find out the delta K, the sum of these four vectors, this four-way mixing process, is equal to 2 pi divided by 8.8 centimeters. So the degree of phase mismatch in the four-way mixing process is given by the product or the median length and the delta K. So with a high atom vapor shell, the median length is about 7.5 centimeter. So the degree of phase mismatch will reduce the generation rate by 1,000-fold. So this is rather big problem in the past. So we figure out this is the problem. So in our experiment, so we use the all co-propagation configuration. That means the coupling field, the Planck field, the signal photon, the pro photon, all propagate in the same direction. So we work out this delta K again. Again, it's consists of two absorption emission process, absorb the Planck photon, emit the signal photon, absorb the coupling photon, emit the pro photon, and the result is just give you 0. Okay, that means the generation rate in our high atom experiment can be 1,000-fold enhancement than the previous result. And also, because this all co-propagation scheme, all the laser beams have a very good overlap with the single photon, the decoherence rate in our system can also be reduced. Okay, so all co-propagation scheme is nice. However, there's a very severe problem because this coupling laser light and Planck laser light has the power up to 40 milliwatt. And the single photon pulse has the power as low as 0.4 picowatt. So there's a 11 orders of magnitude difference between the strong laser light and the very weak single photon. And we want to detect with the SPCN single photon, but not this classical light, the strong classical light. So we need to overcome this severe problem. Fortunately, we developed this polarization filter and the echelon filter. Combine these two filters, we can have a 135 dB extinction ratio. That means we can reduce this strong laser light by 13 and a half order of magnitude. So that's the reason we can utilize this all co-propagation scheme in our high atom experiment. So let's see what we can achieve with our high atom biphoton source. Due to the Doppler effect, the spectral profile or the biphoton temporal profile of the high atom is very different from those of the co-atom. So we first study the EIT spectrum and the biphoton temporal profile as a function of a carbon power. So the left column show the EIT spectrum, and the right column show the coincident count of biphoton. So from top to bottom, with the increasing carbon powers. So we find out as the carbon count become higher, the EIT line width become broader, and the biphoton temporal width become narrower. Okay, and we also fit this data with Lorentz profile and fit this data with a Gaussian profile. Okay, so the EIT spectrum profile is Lorentz. The biphoton temporal profile is an exponential decay, as you can see here. This is dramatically different from the co-atom result, because in the co-atom, as I showed you before, it's just determined by the propagation delay time. However, in the high atom data, it's determined by the EIT spectrum. Okay, and this figure shows the line width of a high atom biphoton source is highly tunable. So we change the carbon power, the biphoton temporal width, or the biphoton line width can be varied by 1 order magnitude. So if we can have a higher carbon power, we can even change the line width. Okay. And also this temporal width cannot be longer. There is upper limit of this temporal width or the lower limit of the spectral line width, because the decoherence rate or the coherence time in the system just limit this result here. So this figure shows longest biphoton temporal profile of the high atom biphoton source. So again, these are the coincident count as a function of delay time, and this is the transmission as a function of the Planck frequency. This is the EIT spectrum, this is the biphoton data. And from the biphoton data, the line width is 280 kilohertz. From the EIT line width, the line width is 300 kilohertz, so they are consistent. So this is the narrowest biphoton line width of the high atom biphoton source, as I mentioned here. So now we can have a very stable and high finesse high atom biphoton source, as demonstrated by narrow line width of its biphotons. So we want to make the our high atom biphoton source more useful, try to increase the generation rate. Okay, so we can increase generation rate by increased carbon power, and it will saturate at some level here. We can also increase the generation rate by increase the pump power or increase the high atom temperature. So higher pump power, you can have a larger generation rate. Higher temperature of high atom, you can also have a higher generation rate. So the experimental data are consistent with our expectation. However, there is no win-win situation, okay? We see here the signal to background ratio. As the generation rate increased, either by pump power or by temperature, the signal to background ratio decreased. And signal to background ratio is important figure of memory of a biphoton source, because it indicates the purity of your single photon. So if your single photon has too much background, that means it's contaminated with some other photon, which is not good. And also, the spectral line width will increase with the generation rate, either by increased pump power or by increased temperature. So that's a narrow line width will result in a higher success rate. Higher success probability of a quantum operation. So larger line width definitely will reduce this success probability. So under the constraint mentioned in the previous slide, so we try to make our high atom biphoton source useful to maximize an important figure of memory called spectral brightness. Okay, and the spectral brightness is defined as a generation rate per line width. That means you can have a higher generation rate and narrower line width. Okay, one can enhance the transmission rate of your single photon or your flying qubit. One can increase narrow line width can increase the success probability of your quantum operation. So this is a combined figure of merit of a single photon source. So in this data, we have a generation rate about 400 kilo pairs per second, and the line width is about 1 megahertz. So this will result in spectral brightness about 3.8 times 10 to 5 pairs per second per megahertz, which is the highest spectral brightness in the world in all kinds of biphoton source. So with this data, I also show you what do I mean about signal to background ratio. So above this dashed line is a heralded single photon we want in the quantum operation. Below this dashed line is the background photon we don't want. So as you can see, because we have a very high generation rate, the background is also very large as compared to the previous line. The background level is very, very low. Okay. So nevertheless, the signal to background ratio is still larger than 3.1. That means our biphoton source violated this Cauchy-Schwarz inequality for the classical line by about 4 folds. That means even with this high background, the biphoton are still non-classical. Okay, this table just showing different biphoton source, and so our co-atom SFWM biphoton source have narrowest line width in the world, and our high-atom SFWM biphoton source have a highest spectral brightness in the world. So both are very nice value we have. So this also, as compared to the other high-atom SFWM biphoton source, so we almost enhance the line width by about 1 order magnitude. So I will give some conclusion because my time is up, I think. So basically, you already know, I mentioned to you, so we can, with the high-atom biphoton source, we can have a line width as narrow as about 300 kilohertz, and the spectral brightness here can reach this the highest value in the world, about 3.7 times 10 to 5 pairs per second per megahertz. So our high-atom biphoton source not only surpass the source produced by high-atom in the previous work, but can also compete with the source produced with the nonlinear crystal and the integrated photonic device. And this high-atom vapor shell has a dimension about 1 inch in diameter and 7.5 centimeter long. So I think this is a rather small device as compared to the co-atom biphoton source. So I will skip these prospects and come to the most important part of this talk to thank my collaborator, Dr. Yin-Chen Chen of the Academic Sinica, Professor Yongfan Chen of National Cheng Kung University, and Zhi Song, the previous speaker, my colleague in National Tsinghua University. So we work together in this single photon generation, and 4 of us, and together with Professor Wendell Liao of National Central University, were supported by this academic summit project by National Science and Technology Council. This is a 5-year project, and this year is the last year. So I also want to acknowledge my former student and the previous students. I think in 2015, we start to build our high-atom biphoton source. And in 2017, I think we observed the biphoton data. Now I think we have one of the best and the state-of-the-art high-atom biphoton source in the world. So they have done a very great, wonderful, and very great job. With that, thank you very much for your attention.
Okay, yeah. Thanks, Professor Yu. Okay, we have time for maybe 1 question, and for the questions asked from online, we'll collect them and have them answered after the conference. So there's one down there. Can someone handle the
Yeah.
speaker? Oh, okay.
Yeah, I can speak through this microphone. In your summary slide, you say there's a 5 times improvement in the single photon line width from, I think, 2 megahertz to 290 kilohertz. What's the reason of that?
I think the all-propagating scheme means our classical light, the carbon and Planck field, and the single photon propagating in the same direction is very important factor in this success. Okay, the reason they still can reduce their system to have a low line width, but they cannot observe it because generation is too low, okay, to make it practical. All right, and second one is because all the laser beam is in the same direction. Again, for the room temperature experiment, the Doppler effect is very severe. So in order to eliminate Doppler effect, all the laser beam and all the single photon have to propagate in the same direction to cancel out this Doppler effect. I think this is also a very important factor in the success here. Okay. Okay, thank you.
Okay, let's thank Professor Yu again for the nice talk.